Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at Moivre's theorem. So it relates to complex numbers. When they're of the form r cis theta, remember that's r cos I sine theta, to the power of n, you can use this formula. As you can probably guess from that, it makes powers of complex numbers so much easier. Let's say we wanted to calculate 1 minus I to the power of 10. Now without this formula, we'd have to expand this, and you know that that is going to take a long time. We'd have to go to the 10th row of Pascal's triangle, there'd be 11 terms, it would take forever. But instead we're going to use Moivre's theorem. Now in order to use it, we have to convert our complex number into the form r cis theta. So here, r is simply going to be the magnitude of the number, square root of 1 squared plus 1 squared, which is equal to root 2. So remember that we find theta by taking the tan inverse of the imaginary part, which is minus 1, over the real part, positive 1. So we end up getting from our calculator minus 45 degrees. Now we have to be careful to note in which quadrant we are. So because the y, or like the sine component, is negative, but the x or cos component is positive, we're in the fourth quadrant. So we have that theta equals 315 degrees. So what we found is that 1 minus I to the power of 10 is equal to r cis theta, which was 315 degrees, to the power of 10. Now we can use Moivre's theorem. It says that if I want to raise this to the power of 10, I can just separately raise the r value to the power of 10, and what will remain, it will be cis n theta. So n is the power, it'll be 315 times 10, which is 3,150 degrees. So root 2 to the power of 10 is just 2 to the power of 5, which is 32. You can use your calculator for that. And then it will be cos of 3,150 plus I sine of 3,150. Once again, you can just use your calculator to do cos and sine of 3,150. So it turns out that cos of 3,150 is equal to 0. It turns out sine of 3,150 is equal to minus 1. So this is 32 times 0 minus I. It's just minus 32i. That was so much easier because of Moivre's theorem. All right, let's now look at roots of unity. So Moivre's theorem is always true whenever the power is an integer. It's only sometimes true when the power is not an integer, but fortunately one of those sometimes involves when we're taking roots. We're going to use this to find roots of unity. That means roots of 1. So here we're going to find the third roots of unity. So that is equivalent to solving this polynomial z cubed minus 1 equals 0. So previously you would have looked at this and said, okay, cool, z equals 1 is the only solution. But now that we know the fundamental theorem of algebra, we know that this here has 3 roots. There are actually 2 other third roots of unity, and we're going to find them out. So we're sort of going to use the opposite of Moivre's theorem. Here, we basically want to raise 1 to the power of a third. So what we're going to do is we're going to first write 1 in the form r cis theta. So hopefully you can see that r is clearly going to be 1. Now what we're going to do is we're going to take the angle 360. So why did we take 360? It's because cos of 360 is equal to 1, but sine of 360 is equal to 0. So this is equal to 1 times 1 plus I times 0. It's just equal to 1. What we're now going to do is we're going to raise each side of this equation to the power 1/3, and then we can use Moivre's theorem. So as I said, Moivre's theorem doesn't always work when the power is not an integer, but it does when we're taking roots. So de Moivre's theorem tells us that we can just raise r to the power of a third, so it'll be 1 to the power of a third, and we can multiply the angle by the power. So it will be 1 to the power of 1/3 cis of 120. So it will be 1 cos 120 plus I sine 120. Now it turns out that's our second root, but it turns out there's a third root, and they're always equally spaced in the arcane plane. So we've got one that's 1 cis 360. We already knew that. That's just one. We've got one that's 1 cis 120. The other one will be where the angle is halfway between these two. So it will actually be 1 cos of 240 plus I sine of 240. So you can just put, if you don't remember, cos of 120 and sine of 120 in your calculator, similarly for 240. So we get these three solutions. The first solution we already know, 1 cos 360 plus I sine 360 is just 1. We knew that that was a third root of 1, but we didn't know these other two here. So cos of 120 is minus a half, and sine of 120, is root 3 on 2. So the other root of unity we have is minus a half plus root 3 on 2. You can probably guess that this will give us the complex conjugate of this. It will be minus a half minus root 3 on 2i. So if you raise any of these numbers to the power of 3, you get 1. So all three of these are roots of this equation. So this actually helps us solve other polynomial equations, which I'll show you now. So it doesn't just help you solve x to the n minus 1 equals 0. We can now solve x to the power of n minus k equals 0 for any k. So the solutions to an equation like this, all of the solutions, you take the nth root of k and you times it by each of the nth roots of unity. So let's say we wanted to solve x cubed minus 64 equals 0. Well, we know the cube root here of 64 is 4, so that's nice and easy. We knew that already, but there are two other solutions. What we have to do is take this nth root and times by each of the third roots of unity. So there's 4 times 1, 4, we already knew that, but we're going to times 4 by minus a half plus root 3 on 2, and we're going to times 4 by minus a half minus root 3 on 2i. They will give us the three solutions. So 4 is the third root or the cube root of 64. We times it by each of the roots of unity. So this one here, we go 4 times minus a half is minus 2. 4 times root 3 on 2, that just gives us 2 root 3. So that's 1. And you can probably guess that this one will give us its complex conjugate. It will be negative 2 minus 2 root 3i. If you raise any of these three numbers to the power of 3, you will get 64. So now we've solved this equation and we know we've come up with all solutions because the fundamental theorem of algebra tells us if it's a polynomial of degree 3, it has exactly 3 roots. There are no more to find. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.